In this video, you will gain additional experience with heat transfer unit operations in Aspen hysys by building a typical preheater train model. Once the rock root is heated and treated, it will enter a section of transfer piping before being sent into fractionation. To model this transfer piping, you will make use of the hysys pipe segment unit to operation. You will also refamiliarize yourself with the balance and adjust logical operations. Finally, you will use the case study analysis tool to study how various independent variables affect certain dependent variables. In order to process a rock crude stream and refine it into usable products, various degrees of preheating and pretreatment must first be applied. In this video, you will construct a preheat train model using a variety of heat transfer unit operations, separators, piping, and logical operations. This video includes the following tasks: build the preheat train, add a pipe segment, install the balance and adjust. Task 1. Build the preheat train. The preheat train will heat and treat a raw crude stream for processing in an atmospheric crude fractionation unit. This raw crude formation is already available as it was defined and computed in the oil characterization and high pressure separation video. This assay file will serve as the basis of your preheat train. Open a new case. Select the petroleum assays folder from the navigation pane. Click the pull-down option of New Assay ribbon and select Import from File. Keep Aspen Text as the assay data format and click the green sign Add button to add an assay. Browse to Root 6 file and click Open. Click Import. Select the assay component Celsius to 850 degrees centigrade. Click OK. Please note that component lists and fluid packages folders are fully defined after the successful importing of the assay file. When you import an Aspen assay management assay into a new simulation case, hysys automatically loads the default hysys petroleum refining component list and selects Bing person as the property package. Now let's go to the simulation environment. Add a material stream. Change its name to rock road. Set the temperature to 15 degrees centigrade and set the pressure to 1000 kilopascal. Set the mass flow to 600,000 kilogram per hour. Select the petroleum assay page and attach existing assay. After selecting assay 1, now the stream is fully defined. In the preheat train and crude processing units, you will need to take into account the presence of water. Add another material stream. Change the stream name to water. Set the temperature to 15 degrees centigrade and set the mass flow to 21,600 kilogram per hour. Set the mole fraction of water to 1. A mixer operation is used to combine the rock root with the water, and the output represents the oil entering the refinery. Further downstream, much of the free water is knocked out using a desalter, which you will model with a three-phase separator. Now add a mixer. Change its name to mixer. Add the rock root and the water streams to outlets. Name the outlet stream to heater. Move to the parameters page and set the automatic pressure assignment to equalize all. By making use of the equalize all pressure option on the mixer, we eliminated the need to define pressure on the water inlet stream. Since the pressure is known in the rock root, the mixer writes that value into all other inlets and into the outlet stream, resulting in pressure equalization at this point of the flow sheet. The preheat train you will build consists of various heat transfer unit operations, separation operations, piping, and logical mathematical operations. First, you will install a simple hysys heater model. Add a heater from the model palette. Change the name to simple heater 1. Set the L stream to 2 heater. Name the energy stream. Name the outlet stream. On the parameters page, set the delta B to 50 kilopascal. The worksheet tab, set the temperature of the two heat exchanger stream to 65 degrees centigrade. Next, a second stage of preheat will be added. This time, you will use the hysys heat exchanger model. The heat exchanger requires process streams on both the hot and cold sides of the exchanger. Before adding the heat exchanger, you will need to define an assumed hot side stream. The hot side stream will be a bump around from the atmospheric brood column. Since neither this column nor the bump around stream currently exists, you will make a reasonable initial estimate of the bump around stream. Add another material stream to the flow sheet. Rename it to hot bump around. Click the Define from Stream button. Highlight the rock road stream. Uncheck all checkboxes in the cup stream conditions section except for the composition. You will specify temperature, pressure, and flow rate in the next step. Click OK. Set the temperature to 180 degrees centigrade and set the pressure to 200 kilopascal. And finally, set the standard ideal liquid volume flow to 175 cubic meter per hour. A heat exchanger will be added to continue heating the crude stream. The heat exchanger performs two-sided energy and material balance calculations. The heat exchanger is capable of solving for temperatures, pressures, heat flows, including heat loss and heat leak, material stream flow rates, UA, and other heat transfer parameters. Add a heat exchanger from the model palette. Change the name to heat exchanger. On the tube side inlet, select to heat exchanger. And on the shell side outlet, select hop bump around. Name the tube side outlet to this desolder and name the shell side outlet called bump around. Move to the parameters page and change the heat exchanger model to simple weighted. Set the pressure drop on the shell side to 5 kilopascal and on the tube side to 35 kilopascal. Move to the specs page. You can see that there is 1 degree of freedom shown for the heat exchanger, meaning that one more piece of input is required to solve the model. You will first need to deactivate the UA specification. To do this, click the Activate checkbox for the UA specification to uncheck it. Click the Add button to add a specification. The hysys heat exchanger accepts a wide variety of specification types. You can use the exchanger specification form to create targets for temperature differences, temperature approaches, and UA values, and much more. It's also possible to use the Worksheet tab of the Heat Exchanger property view to simply enter desired hot or cold side outlet temperatures. This flexibility makes it is very straightforward to define the hysys heat exchanger with virtually any fixed conditions. Define a minimum approach temperature for the exchanger. Set the name to temperature approach and the type to minimum approach and the path to overall and the value to 30 degrees centigrade. Now the exchanger is fully defined. Continue by adding a three-phase separator to represent the desalter. Change the name of the vapor outlet to overhead vapor. And the light liquid to crude. And the heavy liquid to desalter water. You can finish the preheat train by adding the last 3 units before the crude enters the transfer line to the atmospheric column. 2 heaters and a pre-flash separator, like the simple heater 1. Both remaining heat transfer units will be modeled as heater unit operations. Add a heater. Rename it to simple heater 2. Set the LS stream to crude. Name the energy stream. Name the outlet stream. Set the delta B to 372.3 kilopascal. And on the worksheet, set the temperature of two pre-flash stream to 175 degrees centigrade. Add a two-phase separator from the model palette. Name it pre-flash. Set the L stream. Name the vapor outlet. And the liquid outlet. For the last operation in the preheat train, add a heater. Name it furnace. Set the L stream to bottom liquid. Name the energy stream and name the outlet stream. Set the delta B to 172.4 kilopascal. On the worksheet tab, set the outlet temperature to 400. This concludes the first task. Task 2. Add a pipe segment. After the preheated crude exits the furnace, it is ready to move on to the atmospheric crude column. However, we will assume that the atmospheric column is situated about an eighth of a mile from the furnace. To simulate the pressure losses that will occur in the line and check for any other fluid phenomena, the hysys pipe segment unit operation can be added. The pipe segment is a very versatile piping operation that allows for single and multi-phase flow, customizable piping geometry, and various heat transfer considerations. Flow assurance capabilities such as slug flow and original velocity calculations further enhance the capabilities of the pipe segment. You can build the pipe segment to whatever level of detail you wish depending on the simplicity or complexity of the piping configuration you are studying. Add a pipe segment. Change the name to transfer line. Set the L stream. Name the output stream. Name the energy stream. On the parameter page, select the Tulsa Unified Model 2 phase for all three orientations. Navigate to the Rating tab. The sizing form allows you to build physical piping arrangement of the pipe segment. Click the Append Segment button. Specify a length of 76.2 meter and an elevation change of minus 3.35 meter. For providing the piping diameter, it's possible to directly specify the outer and inner diameter values. You can see these as value inputs on the rating sizing form. However, it's usually more convenient to define piping diameter based upon standard nominal pipe sizes. These can be accessed rather easily in Aspen hysys pipe segment. Click the View segment button at the bottom of the form. Select Select the pipe schedule as Schedule 40. Click the nominal diameter and select 600 millimeter. The heated crude transfer line continues on into a standard 90 degrees elbow and then into a further run of pipe to meet up with the atmospheric column. You can add these piping items here in the rating sizing form by simply appending additional segments. The pipe segment also allow you to clone copy existing segment, making it is easier to build and define similar piping objects. Click the Append Segment button. Change the fitting of segment 2 to elbow 90 degrees and set the inner diameter to the same value as pipe segment 1. Please note that for fittings, the View Segment button doesn't provide a list of nominal sizes as it did for the regular piping. It's necessary to manually specify the inner diameter in this case. The final run of pipe will have the same diameter of the first run. Only the length and the elevation change will differ. So click and highlight any cell under segment 1 on the rating sizing form and click the clone segment button. Enter a length of 121.9 and an elevation change of 4.57 meters. Change the number of increments for the third segment to 10. Adjusting the number of increments influences the frequency of internal pressure, flow, flash, etc. Calculations performed by the pipe segment. The pipe segment also needs information on how to conduct heat transfer calculations. You can specify a variety of heat transfer related inputs, fixed duty, fixed heat transfer coefficients, or estimated heat transfer coefficients based upon internal and external conditions. Select the heat transfer form. Click on Estimate HTC. Check all four checkboxes at the left side of the form to include all heat transfer contributions. Assume an ambient temperature of minus 9.4, keeping the default insulation type. Enter an insulation thickness of 1.5 inch. Change the ambient medium to air and enter an assumed wind velocity of 11.176 meters per second. As we highlighted in the previous video, the hysys pipe segment featured 5 powerful flow assurance calculation capabilities. These calculations check the physical structures of the pipe itself versus the predicted wear caused by the type of fluid being conveyed. This allows the process simulator to quickly and easily judge the viability of a pipeline over time based on whatever fluid is being modeled. The particular flow assurance calculations that can be performed are as follows: hydrous formation calculation, rate of corrosion due CO2, original velocity, slug flow analysis, and wax deposition. You will investigate the potential for slug flow in the transfer line using this feature. Click the Flow Assurance tab and select the slug analysis. Check the slug calculation box. This concludes the second task. Now to our third task, install, balance, and adjust blocks. Look at the vapor fraction for stream 2 desalter. It should be equal to 0. The feed to the desalter has to be liquid, but it could begin to vaporize given changes in the pressure at the desalter separator. Keeping track of the bubble point temperature of the 2D salter stream would be extremely helpful. The stream parameters on 2D salter are already calculated, so there are no way you can force the stream to calculate a bubble point. However, adding a balance operation allows you to create a second stream which with the same molar flow rate and composition as 2D salter stream but with no vapor fraction, temperature, or pressure defined. Add a balance operation from the model palette. Name it bubble point. Set the inlet stream to desalter. Name the outlet stream bubble temperature. Set the balance type component mole flow. For the stream bubble temperature, set the pressure of 915 kilopascal and set the vapor fraction to 0. We can see that the crude can be heated up to 145 degrees centigrade without forming any vapor. The adjust operation is another logical operation, a mathematical operation rather than a physical unit operation that models a piece of processing equipment. It will manipulate the value of one stream variable, the independent variable, to match a required value or specification, the dependent variable, in another stream or operation. We are going to use this tool to optimize the preheat train by fixing the molar flow rate of light product leaving the pre-flash vessel, which depends on the temperature of the feed stream. Note that the adjusted variable of an adjust operation must always be a user-specified value. Add an adjust operation from the model palette. On the adjusted variable group, click Select Variable. Select the stream to pre-flash and select the temperature variable. On the target variable group, click Select Variable. Select the light product stream and choose the molar flow variable. Specify a target of 200 kilogram mole per hour. Switch to the parameters tab and note the tolerance and the step size values. Tolerance values should be set such that they are reasonable with respect to the target variable value. Too small of a tolerance can make convergence difficult, if not impossible. Too large of a tolerance can result in an inaccurate solution. When considering step size, use larger, though not too large, rather than smaller sizes. The second conversion method works best once the solution has been bracketed, and by using a larger step size, you are more likely to bracket the solution quickly. However, using too large of a step size can cause the algorithm to require more iteration in bracketing the solution. Here, keep the default step size, but change the tolerance to, to 0.1 kilogram mole per hour. When considering the adjusted variable, it's a good practice to provide minimum or maximum value on the parameter form. These minimum or maximum values could correspond to a physical limit, such as a zero for pressure or flow. This will make your model more robust in the case that the adjust becomes unstable. Take note that the minimum and maximum values are optional and may not be necessary for all cases. Click on the Monitor tab, then click Start. Here we can see that the adjust operation converged after 5 iterations, and the adjusted temperature of the two pre-flash stream is 172 degrees centigrade. This concludes our video. Thank you for watching.